Hey, what's up, pre-calculus? Let's get some experience today graphing a rational function from start to finish. We will run this function through every kind of analysis we have learned so far, and then we will put all the pieces together and sketch the graph. I could not be more excited. All right, so clearly it's going to be a lengthy process. We've got multiple steps, but they really boil down to 4 words: asymptotes, intercepts, points, and sketch. Asymptotes, intercepts, points, and sketch. All right, let's take a look at the first little bit of analysis. We're going to determine the equation of the horizontal asymptote. Now, we've learned where we can look for that. I hope you guys remember that chart of information where we compare the degrees. So let's look right here. Degree 2 in the numerator, degree 2 in the denominator. We are going to notice they match, so we will divide the leading coefficients 2 by 1. Our graph has a horizontal asymptote of y equals 2, and we place that on the graph. Okie dokie. Let's look at the next little bit of information. Determine the equation of any oblique asymptotes. Okay, that's going to be easy. None. Remember, oblique asymptotes only occur when the numerator has one more power than the denominator and the division results in a remainder. That is not true here, so dunzo. All right, moving on. We're going to look for vertical asymptotes or hulls. Okay, these are going to come from undefined values in the denominator. Let us take a look at the denominator. Give it a good factor. And we come to the conclusion there are 2 values of x for which this function is not defined. And that means we've got to figure out what happens at these 2 locations. Is it going to be a vertical asymptote? Is it going to be a hull? That is definitely going to be something we'll want to know for the graph. So let's continue with that 4-step plan we learned in part 1 of the notes here. The 2 undefined values. Okay, we got them. Now we simplify the function. Okay, I'm going to factor up the numerator. Please wear your factoring pants to this test, everybody. Without them, oh boy, it's going to be a long, hard process. Okay. All right, we got everything factored. X plus 2, die. And we now know that the simplest way for us to use this function moving forward, I'll just put a box around it so I don't go back to the bigger version of it. From this point forward, all of our calculations, computations, and considerations will be based on the simplified version. All right, well now we got to figure out these 2 undefined values, asymptote or whole. So why don't we evaluate the function at f of -2, evaluate the function at f of 1. Why don't you pause that video? This is review by now, and I'll come back to you. Alrighty, after we do the plugin, f of -2 got me an actual value of -9 divided by 3, or 3. We're going to see a hull at this location. And when I evaluated at 1, I got an undefined value here, and that leads me to believe there's a vertical asymptote at x equals 1. And I've shown these on the graph. And always remember, cancel hull. No cancel vertical asymptote. That connection is just always going to exist. All right, let's look up at part D. We're now moving into the intercepts part of our analysis. We're going to get the y-intercept, and then in part E, the zeros of the function for the x-intercept. Okie dokie, that should be relatively simple. Y-intercept, input 0 for the y. Remember to use the oh so simple form. And if we compute that number, we've got our y-intercept there at y equals 5. Boom! There you go. And for the x-intercept, well, we've learned in the past, of course, to set the function equal to 0. If you think about that division, we definitely don't want the denominator to be 0. We know we did that up here and it was undefined, very bad. So really clear out that fraction and just set the numerator equal to 0. And that will give you your 0 of the function, or your x-intercept will be at 5/2 or 2.5. All right, we can throw that on the graph now too. Okay, all right. We're now, where are we at here? We are done with D. We are done with E. Part F says, sketch the graph if necessary. Find additional points to plot. I don't know if it's necessary here. Check out what we've got. We might have enough to connect the dots already. I do see, based on the location of the hole, the point, and the vertical and horizontal asymptotes, connecting the dots would lead me to a shape like that. And over down here in this other region of the graph, other branch of the shape, using my x-intercept, the horizontal asymptote, and the vertical asymptote, I do get a pretty easy game of connect the dots. All right, so why don't we check out that next example on the last page. Now, before we go and graph this next function, I do just have to give a little flashback to Chapter 1 about odd functions. Functions who exhibit the feature where when we input a negative x in for all of the x's and simplify, we actually get the negative of the function. These functions are symmetric with the origin, which means a couple things. If you have any random point x comma y on your original graph, you'll have the opposite of both on your same graph. Symmetry with the origin also means you can think about it as two reflections. Take this graph, flip it over x and over y, and it generates the same graph. Or you could also think about it as that rotational symmetry, where if you rotate it 180 degrees about the origin, it looks the same. So keep that in mind, everybody. Okay, looking at this function here, following up with that, this is actually going to be an odd function, and we'll maybe catch a little break when we get to the graphing part of it if we remember that feature about the symmetry, about the origin, and maybe we can save a little time. But moving on, let's go through the whole process. Horizontal asymptote. Degree of denominator exceeds degree of numerator, always the same conclusion, y equals 0. All right, there's your horizontal. Do we have an oblique asymptote? No, the numerator does not exceed the denominator by 1. None about OA. Okay, and here's where it gets so hard, it's easy. We want to find the undefined values so we can determine if they become vertical asymptotes or hulls. Okay, we'll try our best to set the denominator equal to 0. We can even move the 1 over, and we can even square. Don't forget the plus or minus, yeah. But what we're going to get out of that is an imaginary number, not real. Now, listen, I know this topic might be difficult, but we're only graphing the real part of this function, the part we can see on the real x number line and the real y number line. We have undefined values that are not real. We are not worried about any of that. No vertical asymptote, no hole. That's all we got to know about that. Okay, So hard it became easy. All right, y-intercept. Easy peasy, everybody. We got that. Substitute the 0 where the x goes, okay? And we get, oh gosh, 4 times 0 is 0 over 1, which is 0. So we finally get something on our graph. And I guess I could have drawn the y equals 0 horizontal asymptote from part A. So again, that might look a little weird to put a point right on the horizontal asymptote, but remember, horizontal asymptotes only really tell you what's going down on the very left end of the graph and the very right end of the graph. They don't give any insight into the regular small numbers in the middle. Okay, moving on to part E, the zeros of the function. We're going to set the numerator equal to 0. And that's going to kind of be a big nothing burger of an event because our x-intercept is the same as the y-intercept, which we already knew. Oh, no. So this has a whole lot of nothing to go on. I know I have to pass through this point. I know at the right end and at the left end I need to get closer to those asymptotes, but I have no idea what's going on anywhere in the middle. Okay, well, why don't we just adhere to this little piece of advice? If necessary, find additional points. Yeah, I think it's kind of necessary. We got nothing else to go on, gang. So it's really just thinking about plugging in some numbers, all right? I'm going to plug in a 1 and a 2 into the function f and compute the y. When I plug in 1, the numerator I'm going to get it 4 times 1 or 4, and the denominator 1 squared plus 1 or 2, so I'm going to get 1 comma 2. When I plug in 2, let's see, I'm going to get in the denominator 8, and in the, numerator will be 8, denominator will be 2 squared or 4, 4 plus 1 is 5, 8 over 5 is like 1.6, okay. I'm getting a little sick of this already. I'm just going to plot these and see what's up. 1 comma 2, 2 comma 1.6. All right. Well, my thought is this, everybody. If I can at least sketch the right end of the graph, maybe I can use the fact that it's an odd function, use that symmetry, and use that to generate the left side of the graph. So I'm pretty sure the right end has to do this. Connect the dots, boom, 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 and then trail off the y values as they get closer to 0. Okay. Well, again, remember for an odd function, and you don't have to do this, but it can just save you some time. If I know 1, 2 is on the graph, without computing, so is 1, negative 2. If you want to compute it, go ahead. And I know if 2 comma 1.6 is on the graph, so is negative 2, negative 1.6. Why don't we plot those? And of course, what we start seeing does begin to resemble the symmetry we expect from an odd function. Again, connect the dots. As you walk towards the left of the graph, the y values get closer to 0. And that is as best of an approximation as we can get to this graph. It is a pretty decent sketch. If we needed it any more accurate, we would consult a graphing calculator or Desmos. But that should give you a little bit of practice of getting through all of the steps, putting them together, and forming a beautiful graph. Well, that's all for now. Ta-ta!